I'm starting with the data. We have two datasets. X, representing gene expression levels with 100 samples and 50 genes, and Y, representing clinical outcomes with 100 samples and 3 outcomes. Think of it like this. Each sample is a patient. X tells us the activity levels of 50 different genes in that patient, and Y tells us 3 different clinical measurements for the same patient. Pretty cool, right? This simply restates that dataset X has 100 rows, samples, and 50 columns, genes. Each cell contains a value representing the expression level of a particular gene in a particular sample. I'm picturing a spreadsheet here. Similarly, dataset Y shows 100 samples and 3 clinical outcomes. Each row represents a patient, and each column represents a different clinical measure for that patient. Maybe things like blood pressure, heart rate, and cholesterol levels. Here, we're using partial least squares singular value decomposition, PLSSVD, a technique to find relationships between X and Y. We are setting in underscore components to 2, meaning we want PLSSVD to find 2 main directions that capture the shared variance of these two datasets. Think of it like finding 2 key factors driving the relationship between gene expression and clinical outcomes. PLSSVD is a fancy dimensionality reduction method. After running PLSSVD, we get transformed datasets. These are lower dimensional representations of X and Y that capture the essence of the relationship found by PLSSVD. The original gene expression data, X, is now reduced to 100 samples and only 2 components. This means PLSSVD has captured the most important information from 50 genes into just 2 new variables. We've reduced the complexity. It's like creating a summary of the original dataset. Likewise, the clinical outcomes data, Y, is now expressed using these same 2 components. This helps us compare the reduced gene expression data, X_transformed, and the reduced clinical data, Y_transformed, more easily. The question is to determine which statements are true about the results obtained by PLSSVD, specifically focusing on the shape and interpretation of the transformed datasets, X_transformed and Y_transformed. Time to put on our detective hats. This statement is about the dimensions of the transformed datasets. Because we chose 2 components, both X_transformed and Y_transformed have 100 rows, samples, and 2 columns, components. It's a direct consequence of choosing in underscore components equals 2. I'm looking at 2 datasets. X represents gene expression levels, and Y represents clinical outcomes. Think of X as a table with 100 patients, rows, and 50 different genes measured for each patient, columns. Y is a similar table, but instead of genes, it holds 3 clinical outcomes for each patient. We want to see how these 2 things relate to each other. This is just clarifying the shape of the X dataset, 100 rows, samples or patients, and 50 columns, genes. Similarly, this specifies the shape of the Y dataset. There are 100 patients and 3 different clinical outcomes measured for each. I'm using partial least squares singular value decomposition, PLSSVD. It's a fancy statistical technique that helps me find relationships between my 2 datasets. I'm setting n_components to 2, which means I want to find only the 2 most important features that explain the relationship between the gene expression data, X, and the clinical outcomes, Y. PLSSVD gives me back 2 new, latent variables. These aren't things I can directly observe like gene expression or clinical outcome. Instead, they represent the hidden patterns or relationships between X and Y. These 2 latent variables capture the covariance, essentially, how much the genes and clinical outcomes change together. Think of it like this. I am trying to distill the essence of the relationship into 2 key features. This section introduces a multiple-choice question that tests your understanding of partial least squares singular value decomposition, PLSSVD. I'm testing whether you understand how PLSSVD transforms data and what the results mean. Get ready. This question asks you to evaluate several statements about the output of a PLSSVD analysis, focusing on the shapes of the transformed datasets and the relationships between them. This is the first option, saying that after using PLSSVD with 2 components, dataset X, initially, 100, 50, will become 100, 2, and dataset Y, initially 100, 3, will also become 100, 2. I'm checking your understanding of dimensionality reduction. Let's see if you got this right. This last option says PLSSVD focuses only on explaining variance in Y, ignoring X. That's not quite right. Think about what PLSSVD is trying to achieve. It's all about finding relationships between X and Y. PLSSVD looks at the shared variance between the two. This statement accurately describes the meaning of an underscore components in PLSSVD. It's saying the two components represent underlying factors explaining the relationship between X and Y. The covariance is key here. How much X and Y change together? This option suggests the transformed datasets will be unrelated, but PLSSVD aims to do the asterisk opposite asterisk. Maximize the relationship between them. I hope you remembered that. We start with two datasets. X, representing gene expression data, 100 samples, each with measurements across 50 genes, and Y, showing clinical outcomes for the same 100 samples, with 3 outcome measures for each. Think of it like this. I have information on 100 patients, 50 measurements about their genes for each patient, and 3 clinical outcomes for each. I want to see how these relate. This dataset, X, is a matrix with 100 rows, 1 for each patient sample, and 50 columns, 1 for each gene. Each cell shows the expression level of a particular gene in a particular sample. It's like a spreadsheet. I have 100 patients and 50 genes that I've measured. Similarly, Y is a matrix with 100 rows, same patients, and 3 columns, 1 for each clinical outcome, for example, survival time, tumor size, etc. Each cell shows the clinical outcome for a particular patient. I'm looking at 3 clinical parameters per patient in this dataset, which is another spreadsheet. I'm using partial least squares singular value decomposition, PLSSVD, a dimensionality reduction technique, to analyze the relationship between X and Y. The n underscore components equals 2 part tells the algorithm I only want 2 new variables that capture the main relationship between gene expression and clinical outcomes. I'm essentially making the data simpler to understand. After applying PLSSVD, I get 2 new datasets. X underscore transformed and Y underscore transformed . These are lower dimensional representations of X and Y, respectively, reflecting the core relationship between the two. X underscore transformed retains the 100 samples from the original gene expression dataset, X. But I've reduced the number of variables, genes, to just 2 components. These components summarize the information from the original 50 genes. Similarly, Y underscore transformed keeps the 100 samples from the original clinical outcome dataset, Y, but also reduces it to 2 components, representing the 3 original outcomes in a simpler way. These 2 components, in both X underscore transformed and Y underscore transformed, are the latent variables. They're the hidden factors that best explain the shared variance between the gene expression data, X, and the clinical outcomes, Y. They're like simplified summaries of the original, more complex data, aiming to show how the clinical outcomes relate to the genes. The goal of PLSSVD here is to find these 2 latent variables that capture as much of the covariance, a measure of how much the 2 datasets vary together, between X and Y as possible. I want to see what information these 2 variables capture about how genes and clinical outcomes covary, that is, change together. I see that dataset X represents gene expression data. It's a matrix with 100 samples and 50 gene expression measurements for each sample. Think of each row as a patient, and each column as a different gene. This dataset, Y, contains the clinical outcomes for the same 100 samples. It has 3 different clinical outcome measurements per sample, such as maybe survival time, tumor size, and a disease severity score. We're using partial least squares singular value decomposition, PLSSVD, to analyze the relationship between X and Y. The parameter n underscore components equals 2 tells the algorithm that I want to reduce the dimensionality of both datasets to 2 components. These components will capture the main relationship between the gene expression levels and the clinical outcomes. It's like squeezing a lot of information into two more manageable dimensions. This is the transformed version of the gene expression dataset after applying PLSSVD. Because n_components equals 2 it will be a 100 samples by 2 components matrix. Each row will represent a sample, and now, instead of 50 genes, there will be only 2 features representing the most important information concerning the clinical outcomes. The shape, 100, 2, means 100 rows, samples, and 2 columns, components. Similarly, this is the transformed version of the clinical outcomes data. Like X_transformed, this will also have only 2 components. I expect it to be a matrix of 100 rows and 2 columns. Again, this is the shape after applying dimensionality reduction using PLSSVD with n_components equals 2 . It is 100 samples by 2 components. I'm starting with 2 datasets. X represents gene expression data. Think of it as 100 samples with measurements across 50 genes. Dataset Y holds clinical outcomes, 100 samples with 3 different clinical measurements each. We want to find relationships between these datasets. This dataset X has 100 rows, samples, and 50 columns, genes. Each cell represents the expression level of a specific gene in a given sample. Similarly, Y has 100 rows, same samples as X, and 3 columns, clinical outcomes like disease stage, survival time, etc. I'll use partial least squares singular value decomposition, PLSSVD, a dimensionality reduction technique. I'm setting the number of components to 2, meaning I want to find 2 main underlying factors that explain the relationship between X and Y. PLSSVD will uncover 2 latent variables. These variables are combinations of genes, from X, and clinical outcomes, from Y, that capture their main correlated variations. They represent the most significant patterns relating gene expression to clinical outcomes. After applying PLSSVD, I'll have new, smaller datasets. The transformed X dataset will still have 100 samples, but now only 2 columns representing the projections of the original gene expression data onto the 2 latent variables discovered by PLSSVD. The same holds true for the transformed Y dataset, 100 samples, but only 2 columns representing the projections of the clinical outcomes onto these 2 latent variables. It's a more compact representation, capturing the essence of the relationship between X and Y. I'm looking at 2 datasets. X represents gene expression levels, with 100 samples and measurements for 50 genes. Y shows clinical outcomes for those same 100 samples, each with 3 different outcome measures. Think of it like this: each row is a patient, and the columns are their gene expression levels, X, and different health indicators, Y. This is just a more detailed description of the X dataset from the previous row. We have 100 patients, and for each patient we've measured 50 different genes expression levels. Similar to the previous, this gives us the details of the Y dataset. For the 100 patients, we have 3 clinical outcome measurements, like maybe blood pressure, heart rate, and cholesterol level. Here, I'm using partial least squares singular value decomposition, PLSSVD. It's a fancy technique to find the relationships between the gene expression data, X, and the clinical outcomes, Y. The n_components equals 2 part means I want to reduce the complexity of the data down to just 2 main components, 2 underlying factors that explain most of the relationship between X and Y. These 2 components are called latent variables. They represent hidden factors that capture the relationship, the covariance, between gene expression levels and clinical outcomes. I'm essentially saying, I believe that these 2 hidden factors are largely responsible for the relationship between what I see in X and what I see in Y. After PLSSVD, my original gene expression data, X, is transformed into a smaller dataset, X_transformed. Now it has only 2 columns which represent the values for those 2 main hidden factors for each patient. I've reduced my data from 50 gene measurements to only 2, capturing the essence of the relationship with Y. The same thing happens with the clinical outcomes, Y. PLSSVD transforms it into Y underscore transformed, also with 100 samples and 2 components. These components align with the ones from X underscore transformed, reflecting the shared variance between X and Y.